Welcome to The Explainer. Today, we are pulling back the curtain on the incredible world of massive industrial automation. We're going to explore the high-stakes engineering that keeps our essential infrastructure running smoothly, even when there isn't a human being around for hundreds of miles.
So, picture this. You've got an enormous 48-inch pipeline station pumping staggering quantities of liquid, and it's completely isolated out in the absolute middle of nowhere. How do you control something that massive entirely automatically? If something goes wrong out there, you can't exactly just send someone down the hall to flip a switch, right? It's a massive, high-stakes engineering puzzle. The entire system has to be self-sufficient, completely fail-safe, and capable of making critical, split-second decisions without any human intervention whatsoever.
Okay, let's dive right into this. Our agenda today covers automating a remote pump station, sensors and the control system, the brain, which is ladder logic, the face, HMI design, decoding signals with DAQ, and finally, the blueprint. Section 1. Automating a remote pump station. Our mission here is pretty clear. Build a totally self-sufficient, fail-safe system in absolute isolation. To pull that off, we rely on a few core components. First up, you have a gas turbine acting as the primary mover. Its job is to physically push liquid through that massive 48-inch pipeline pump. But here's what makes this setup incredibly ingenious: its self-sufficiency. Because it's so incredibly remote, it cannot rely on a city power grid. Instead, it uses a heat recovery boiler to capture the exhaust heat from the gas turbine itself. That exhaust heat creates steam, which then drives a steam turbine generator to produce independent electrical power for the entire station. It is just a brilliant closed-loop survival mechanism. Moving on to Section 2, Sensors and the Control System. If you think of those heavy turbines as the muscles of the operation, well, these sensors are absolutely the nervous system. They allow the station to actually feel the physical world around it. The system requires extreme sensitivity, and it gets that through instruments like Type E thermocouples for reading extreme heat, 420 milliamp pressure transmitters for the boiler, and vortex flow meters for the pipeline. Without these highly sensitive instruments constantly feeding data back, the control system would be completely blind. Literally, a tiny pressure spike or a really subtle temperature rise would just go totally unnoticed until it caused a catastrophic failure. So you might be wondering, how does it process all those physical feelings? Enter ladder logic. This is a programming language used heavily in industrial automation, and it visually resembles old-school electrical relay circuits. It's essentially a set of strict physical rules that have been converted into digital code. It takes all of those raw sensor inputs we just talked about and translates them into safe, sequential outputs. This is exactly how this massive organism thinks. Section 3. The brain. Ladder logic. This logic is where we program the station's strict rules for survival. Let's look at a standard startup command. In step 1, the operator initiates the start button, but the pump doesn't just immediately fire up. No way. In step 2, the logic acts like an incredibly strict security guard. It checks the emergency stop status and heavily scans the system for any active alarms. It absolutely refuses to start unless every single safety interlock is cleared. Only in step 3, if everything is totally perfect, does the pump running coil finally activate. And let me tell you, those safety interlocks, completely non-negotiable. For instance, the burner tap will open only if the boiler temperature is already sitting above 200 degrees Celsius. The pump, it only starts if the gas turbine is over 700 degrees. But let's play out a what-if scenario. What if a valve gets jammed and that boiler pressure suddenly spikes to 50? Instantly, the logic triggers a fault alarm. What if the turbine suddenly hits 850 degrees? Boom, alarm. The main takeaway here is that these specific logic rules are the absolute lifelines, preventing this heavy machinery from literally tearing itself apart.
Section 4. The face. HMI design.
Now we move to the Human-Machine Interface, or HMI. This is the face where the digital brain actually communicates with its human operators. In standard operating mode, everything is calm and collected. The running status is active, parameters are within safe bounds, and the interface itself is deliberately simplified. There's no unnecessary clutter to distract you. But compare that to the emergency stop mode. Instantly, the pump shuts down. Every single control button except the reset function is completely deactivated, so nobody makes a bad situation worse, and stark visual and audio alarms are triggered. This brilliantly illustrates how good interface design manages cognitive load. It keeps things super simple when everything is fine, and completely locks down the system while pointing right at the problem during an emergency. Section 5. Decoding signals with DAC.
Okay, let's talk about the translator of our system, data acquisition, or DAC. This is what converts microscopic, real-world analog signals into digital math the brain can actually read. And picking the right translator really matters. Our system needs to read thermocouple sensors across a 20-volt range, meaning from negative 10 volts all the way to positive 10 volts, because temperatures out in these isolated environments can plummet well below freezing. If we use a 12-bit DAC, that 20-volt range gets divided into 4,096 digital steps. That means the absolute smallest change it can possibly read is 4.88 millivolts. But watch what happens with a 16-bit DAC. It divides that exact same 20 volts into over 65,000 steps. That lets it read a tiny change of just 0.305 millivolts. The 12-bit system is just way too blunt. A 16-bit system is absolutely required for this level of extreme precision. But here's the catch. Even with a fancy 16-bit system, those raw sensor signals are still too weak. They have to be amplified. But there's a hard limit to how much we can turn up the volume, and that limit is 205. This number is the absolute maximum amplification gain allowed. Why? Well, because the maximum raw voltage from our thermocouple is 47.78 millivolts. If we amplify it by any more than 205, the signal will physically push past the 10-volt limit of our DAC. It will saturate, clip the data, and will completely lose our critical temperature readings.
On the flip side, what if we need to detect a microscopic 3.4 microvolt change? And trust me, we do, because a change that small could signal the very beginning of a bearing failure in the turbine. To see that with our 16-bit DAC, a minimum amplification gain of 100 is absolutely required. So bringing this math back to the real world, dialing in this precise gain sweet spot between 100 and 205 ensures that our automated system never, ever misses a critical temperature fluctuation. Section 6, the final blueprint. Bringing this whole massive puzzle together requires a piping and instrumentation diagram, otherwise known as a PNID. A huge system like this needs a universal language so that engineers anywhere in the world can instantly understand it. That's exactly where ISA 5.1 standards come into play. On our blueprint, you aren't just looking at a drawing of a pipe. You are seeing standardized tags mapping the physical world to the software. TT stands for temperature transmitter, PT is a pressure transmitter, LIC is a level indicating controller, and FCV is a flow control valve. These tags act as the ultimate blueprint for the entire integrated network. And when you look closely at that blueprint, it reveals a really brilliant hybrid architecture. For raw, unhackable reliability over long distances across the facility, it relies on old-school 420 milliamp analog signals. But for the digital brain to actually talk to the outside world, it uses modern Modbus TCP and OPC UA protocols. Mixing this rock-solid analog reliability with modern digital integration guarantees both the physical safety at the site itself and incredibly secure real-time SCADA monitoring from literally anywhere on the globe. Which leaves us with this final, really exciting thought. Today, we have these incredibly advanced, fail-safe ladder logic setups and hybrid networks doing the heavy lifting. But as we look ahead, how will the integration of the Internet of Things and AI-driven predictive maintenance, systems that can quite literally fix themselves before a human even knows an alarm was going to trigger, how will that ultimately reshape the entire future of industrial automation? It's a fascinating space to watch. Thanks for joining us on this explainer, and we will see you next time.